I'll have to record the beginning again. Yep, so most of you, I hope, have completed this. It's very quick. So basically my largest velocity in the system is the one on the bottom plate. The smallest velocity in the system is the zero or the top plate. And what do I have in between? Linear change. Line would be the profile. So basically all of these vectors are getting smaller and smaller as I'm getting to the top plate. Okay? So this is basically the basic thinking that Newton did. He did a whole lot of thinking. So he then tried to quantify this. Okay, so this observation. So okay, I have A as my areas of the plates, and there is a separation between the plates. Okay, so I have essentially three variables in the system, Vx, A, and Y. And if I'm thinking about the force that I need to exert on this bottom plate to maintain this situation in steady state, okay, what is that force going to be proportional to? Velocity, so the larger the velocity, the larger the force I need. Okay. What about separation?
Inversely.
Okay, and so they basically the smaller the separation, the larger the force. And then what about A? Area. Proportional as well. So basically with those simple observations, okay, when I put that together, okay, essentially I will divide by area to get a tensor, okay. I will throw in a coefficient of proportionality, okay, and then I'll also recognize that I'm going to look at this change in velocity as a velocity gradient, okay. So how do I look at that? Well, okay, my definition of a derivative in this case, this is a very simple case where I have only one velocity that is non-zero. So when I look at its derivative in y direction, I have the value at y minus value of 0 over the separation, which is y minus 0, right? So this is my derivative. So this is where minus comes in, because in our coordinate system, my largest velocity is at the 0, and my smallest velocity is at top plate, right? 0 minus Vx. So I will get that f over a is, this is my coefficient of proportionality, minus dvx dy, if I now talk in terms of derivatives, or if I wanted to maintain the same notation, this would be delta Vx over y, right? The uppercase y. So it's a very simple observation. What I don't know, I throw into this bucket called coefficient of viscosity, quite literally. Okay? So I'm assuming very simple relationship, and I have a fitting parameter. And I can look at my experiments, and a lot of experiments will actually comply to this, and this will be very well valid. And for everybody else, I might still use it even where it doesn't apply, in which case I will refer to this as effective viscosity. So I might actually have a fluid that doesn't comply with this, and it's non-Newtonian. Particulate fluids come to mind, so if I have a lot of solids within the fluid, that will come into picture. So I might nevertheless still talk about effective viscosity of that system, but basically when I fit experiments to this particular relationship, right? So I have all of the measurements I need, so I can come up with this effective viscosity value. All right. So I can look at this in multiple ways. And now I will actually break this down into, I'm actually now, so this was a very simple situation where I had velocity Vx that was non-zero in one of the directions and 0 in all of the others. So it's a very simplifying situation. Okay. My gradient was also kind of active only in one coordinate direction, that was y. So I had only one non-zero velocity, which is x velocity, right? And only one sort of non-trivial direction, which was y direction. Okay. Now I have to try to look to extend that to a more general situation where I have one velocity over there, which is whatever it is, and it has 3 directions, and one velocity over there, and this is not my coordinate direction, but just some general direction. So how do I actually go and get there? So we will first just define this in a more general sense. So I will look at the direction of the force exerted by this. So if I'm looking at this lower box of fluid, right, and upper box of fluid in my system, overall, I see larger velocities here and smaller velocities here. Right? Because of that, the fluid underneath will sort of pull the top fluid. I will feel the shear force, and that's precisely that force that I'm talking about. It's shearing force. Okay? Normal force, shearing force. So this contact force here, I'm looking at its direction, so its direction is in this direction because I'm shearing. So I can define this whole business inside the fluid as at any point, what is the force that this sort of lower box of fluid exerts on the top box of fluid, and then I can of course look at the infinitesimally small boxes. So that's how I'm gonna define this force everywhere, and not just this force that is needed for the bottom plate to keep going. Right? So I can then extend that to the general case. So this is the force view. Now, if I'm looking at the momentum transfer, what is a momentum? Everybody did their chapter 0 reading over the weekend, right? Right. So if I have exchange of momentum, momentum is mass times velocity, right? So obviously, these particles here have larger momentum than the one on top. Okay? So what is the direction of the momentum transfer in this particular case? So they will, through collisions, they will share their momentum. What's going to be the general direction of average in y direction? Okay. So my momentum is actually going to transfer in y direction, even though the force is felt in x direction. Is everybody clear on the two concepts? Okay. So basically, in this force perspective, my flux tau yx, which is force divided by area, okay, is the force in x direction, okay, exerted by this lower portion of the fluid in y direction, so lower y portion of the fluid up onto the higher, greater y portion, okay, per unit area. So it's basically things are orthogonal to the y direction. Now, if I'm looking at the momentum perspective, the same tau yx, okay, it's x momentum of particles transferred in the positive y direction. Again, per unit area, orthogonal to that y direction. Okay. So momentum is transferring in y direction, force is felt in x direction. Okay. And this flux happens because I actually have gradient in momentum. Now, if I actually think about it a little more, my tau yx is minus y. Let me actually work with the mouse so it's recorded on the movie. So you have tau yx is minus mu dvx dy. If I divide by rho and throw in, rho is my density of fluid, and throw it in there, okay? I can do that because I'm assuming a constant in this particular case. Then I'm actually having a gradient in momentum, okay? And this coefficient becomes just another coefficient, but it's kinematic viscosity. So this is sort of the momentum view of the Newton law. Okay? So we have two possible perspectives. Final perspective comes from basically electrical current. So the gradient of velocity is the driving force of this system. Okay? Just like difference in voltage would be in electricity. And my 1 over viscosity is the resistance to it. Okay? So I can look at this flux tau yx as my driving force, which is my gradient, divided by resistance. Okay? So this is just an alternate views of the same thing. Okay? So all of this is pointing actually to a family of what we call empirical laws. And empirical law means that, well, Newton observed it, concluded that he can actually find a very simple law. This law relates flux and gradient in velocity. And we mentioned that in our introduction. We're looking for these relationships that are relating flux to gradient of something. Darcy's law is one of them. Okay? Okay? So when observed, it was simply a law. And then you can actually look at, well, how many times this is actually occurring. So these laws were initially guesses. Okay, it seems that nature works this way. Okay? Let's observe it some more. So first, as Richard Feynman pointed out in that little movie I played, first you guess, then you actually compute and see how different your guess is from what you actually measure, right? And you compare to those measurements to see how good your approximation is. And for those fluids where this observation is good, we call them Newtonian fluids, okay? And all others are non-Newtonian. So these are just to point out some other laws, just so that you see this simplicity in flux versus gradient relationship. Fourier's law, and I'm pointing out the years too, so you can actually see how in history those things were thrown in. We now come to see, transport is difficult to study, and when you think about it, well, of course it's difficult to study. It took 3 centuries to develop, okay? So it's not something, especially when we get to tensors, it took 150 years of calculus development to actually get to the point that we now find difficult to master in 1 week, supposedly, okay? So give it the historical perspective and you will have a better appreciation. So after Newton, Fourier came along and basically looked at the similar thing just for heat transfer. So if I have, again, 2 plates, now I don't have a moving fluid, so situation is actually simpler the moment I don't have moving fluid, moving parts. And I keep one at one temperature and the top plate at different temperature. And as I do that, I will observe heat flux. And this flux, again, I can look at the heat per area, okay, is proportional to the gradient. That means that it's proportional to the difference in temperature, inversely proportional to the separation. And my coefficient is, in this case, K, or thermal conductivity. Okay? So basically, we will see similarities in all different types of transfer. So can you actually draw this for yourself on a piece of paper? And for momentum and heat transport, fill in what is my potential difference in, what is the driving force or the gradient I'm looking at, how do I call the flux quantity, and what is the transport coefficient involved. So I kind of touched upon all of those, so this is just to see whether you're paying attention. So here's, you can check on yourself. So potential differences in velocity or momentum, you could have put in mass times v here. And for heat, that's in temperature. Driving force is gradient in velocity and gradient in temperature. The flux I'm going to refer to as tau, stress tensor, and heat flux. And coefficients are viscosity and thermal conductivity. Mathematically, what does gradient be? What object, if I'm computing it? If you were in calculus class and I had a 3D velocity, the 3. What is it mathematically? How do I write it down?
3 by 3 matrix.
3 by 3 matrix. So yeah, we'll get to the types of derivatives later. Okay, so that's related too. So this is a 3 by 3 matrix because I have 3 different velocities and 3 different directions. I could look at the partial derivative, right? So this is Jacobian. Yes? Calculus? Now rings a bell? All right. So this is a tensor quantity. This is a tensor quantity as well. So we have just defined only tau yx, right? But there's tau xx, tau xy, tau xz. Tau yy, tau yz, tau zz. Those are the unique ones. And then my tau yx is the same as that tau xy, right? So I have 9 possible velocities. Heat transfer is much easier in the sense that I have gradient in temperature, and temperature is scalar. So gradient in temperature is a vector. Okay? So my flux is a vector as well. So in that sense, this is a much easier transport. Good luck in reality, you have both. Okay? So we will actually learn how to decouple them, but technically, even if one of them is simpler, typically for us there's fluids moving. If there's no fluids moving, nothing's happening. So if I have heat transport, I typically have some fluid moving too, so there will be both momentum and heat transport. Okay? So essentially, those are the differences. So this is somewhat, if I'm dealing with this one in isolation, it's simpler because as my essential quantity are vector versus tensor. Okay. Now this one is actually, this one came before heat or before Fourier's law, Hooke's law. So I have a similar case if I extend a little spring, okay, by delta x, the restoring force will act in opposite directions, so I have a minus. And again, I have a coefficient relating to it, so it's minus k delta x. Now this can actually be generalized for a solid beam. So if I'm sort of extending the solid beam using a shearing force, I'm going to relate the shear stress to strain. So we have stress-strain relationships typically in solid mechanics. And my shear modulus, so now shear modulus has different, what are the units of this? Same as stress. So if this is in pascals, this is in pascals as well. Typically in gigapascals, but that's a different story. Okay. So basically, I have, because this strain does not really have units, they're normalized. Okay. So I have a similar generalization there. And finally, Fick's law. So this is essentially diffusion of particles. So if I have difference in concentration field again is scalar field. Okay. So my calculations will actually be simpler because my quantity that I'm looking at, the flux that I'm looking at, is a vector, not a tensor. But now I'm looking at the mass flux, J, and it's also diffusing if I assume larger concentration at the bottom. So let's say that I have some diffusing substance, for instance, helium, and this is some silica wafer, and so there's no any fluid motion here going on. And I'm just diffusing up to the top plate, and my top plate is maintained at 0 concentration, for instance, with a fan or something of that sort. Okay? So basically, then I'm gonna experience again flux in y direction, okay, and it's going to be related to the gradient in my concentration by diffusivity. So diffusivity is the coefficient that I have in mass transport. So all of those are similar. And of course, Darcy's law that we already looked at before. I have now gradient in pressure This is my volumetric flux, so it's basically meter cubed per second. And then I have two coefficients. So this is a porous medium. One of the coefficients is describing my porous medium geometrically, that is permeability. So my absolute permeability is sort of the geometric quantity that describes what is the geometry that I'm going through and how tortuous it is and how porous it is. Okay? And I'm sort of separating that from viscosity of the fluid, or rather I'm behaving as if it was independent of viscosity, and whether I use gas or I use liquid, I'm going to get the same measurement. Of course, I actually know, if I study petrophysics a little, more, I will actually learn that I have to correct the equations because gas permeability and liquid permeability are not the same thing. But nevertheless, fundamentally, as a concept, we are behaving as if they were, because otherwise we cannot easily make effective measurements. And basically, I'm relating my flux to gradient in pressure. So pressure is my potential in this particular case. Okay. Finally, Ohm's law, same thing. I have difference in voltage. Okay. So I'm again looking at the current, electrical current per area. Okay. And I have gradient in voltage in y direction. And this time, my coefficient is conductivity. Okay. Minus always shows up as an orientation thing. Of course, in nature, physically, I'm always going to flow from more of something to less of something, right? All of the coordinate systems that I know are oriented from less of something to more of something. They all start at 0 and they're pointing to more of something. So whenever I'm flowing from more of something to less of something, I better flow in the against my coordinate system. And that's why minus shows up. Does that make sense? Okay. So that's essentially, and that's what showed up originally in that Newton's law. So my coordinate systems, they go from 0 to something larger, but my flow doesn't obey. So integrated form of this is more famous. So basically, I'm just going to multiply by A and have, like, this is voltage is my difference in potential. And this overall will be called 1 over resistance. So we know that V is equal to IR. That is famous Ohm's law. So it's better known as such. Again, all of these laws have very similar fundamental concepts behind them. So back to our viscosity. So now that we figured out, okay, we figured out viscosity, we figured out that all of the transports to a first approximation behave the same, okay, or are approximated in the same way. Let's now get back to the viscosity and what are the units that we're going to look at. I don't like memorizing things, so the only thing that I like memorizing is the fundamental concept. That's that tau yx is minus mu dvx dy. Okay. From that, and any time of the day, if you wake me up at 2 a.m., or it happened last night, if my baby wakes me up at 2 a.m., I can think about viscosity by trying to rock him back to sleep. And then I can calculate that my units of my viscosity, okay, are those of stress, which is Pascal, Newton over meter squared. That's that force per area system, divided by differential in velocity, so meter over second times 1 over meter. So that will give me Pascal second. Okay. So that is the SI system unit that I learned first and I love for its simplicity. But reality teaches us that we have to engage in other complicated systems. So one of them is CGS. That one's not too bad. I just have dimes for the force per centimeter squared. So basically in systems where meter per second is too big of a velocity, and that's probably true for most of the porous media, it's more practical to use CGS units because just the sizes of the systems are more into centimeters, centimeter per second, and so forth. So in CGS system, I will get poise, so I can actually look at the How do I convert that? So basically 1 Newton kilogram is 1,000 grams, so this is centimeter gram second, right? 1,000 grams, 10 to the square centimeter over second squared. So you will get that Newton and Dean are related with 10 to the 5. So then 1 poise is 0.1 Pascal second. And most often we will use centipoise because water has viscosity of 1 in that system. So that's something that is easy to remember, right? So water is 1 centipoise, and that's 10 to the minus 3 Pascal seconds. So this is worth remembering. Okay, this relationship and that relates to viscosity of water. Now, British system, I'm totally in love with that one. 1 pound per foot squared. This is pound mass as opposed to pound force, right? Times foot over second squared. Yeah. Times 1 over foot second. So this is basically my stress, and over feet over second times 1 over foot. So you will get pound mass over foot times second. I never remember conversions for these. Good news is BSL has all of the conversion coefficients if you're into that. Okay. So calculating quickly back and forth, you kind of have to live with it. You have to do it. All right, so those are all of the systems we're going to look at. Now, true or false? Viscosity of liquids decreases with temperature. True. If you're into breakfast or elaborate breakfast in the morning, you heat up some oil or some other grease of your choice, and you will notice that it's going to move easier in the pan just before you put eggs on it, right? As you increase the temperature. Is the same, so that for liquids, viscosity indeed decreases with temperature. How about gases? A couple of you said false. Any other opposing opinions? It is actually false. So with increasing temperature, I'm gonna increase number of collisions. And that's actually going to result in increased viscosity. Now, those are experimental observations. There is a table 112 in BSL for air, and basically temperatures from 0 to 100 degrees. And you can actually see this is sort of a linear increase for this particular fluid. And for liquids, for water, similar types of temperature ranges, and basically if you plot those, you will see that it decreases. So these are experimental observations. I'd like to explain them in some fundamental way. Okay, I would like to know what is the mechanism behind this observation. Again, viscosity is my catch-all coefficient. Okay, it's something that I'm looking at from the outside. It's like, okay, I'm fitting it to viscosity when I'm measuring it. I'm fitting it to the particular model that I assume, like Newton's law. Okay, like actually, well, depending on the type of viscosimeter you use, but there is a law behind it that you assume. Okay. So when you're fitting it, when you're measuring, it's just sort of this macroscopic outside observation. What is the actual mechanism of that? So for that, we need to look deeper into molecular theory to actually find that theory. And that is our next topic. So basically so this is the first introductory part, and now we're moving on. So this was basically the reading that is corresponding to what I just went over. It's chapter 1.1 in transport phenomena. I'm constantly referring to the book as BSL, Bird, Stewart, Lightfoot. And everybody does, so you kind of have to just start with, BSL, right? Everybody, that's what BSL meant. It's not a unit of viscosity. It's a book, it's a textbook. And then our next chapter, so we're actually jumping to now 1.4 to actually look at this theoretical considerations. We will get to all of the chapters, okay? It's just that I wanted to delve into this first before going to the tensor description of the stress, because that's a little more hairy. So basically, we will get to all the chapters. You can read the first chapter basically from the beginning to end, but we'll just do them in different order. Okay. So now we will move on to the molecular basis for viscosity. This is my progress report. Okay. So first, there are two chapters that are dealing with it. One is chapter 1.4 and the other one is 1.5. So I will basically start chapter 1.4 just as fundamentals and overview. Then I'm going to ask you to read it through, and next time we'll actually write things down. Okay? So today I'm just going to give a general overview. So again, I'm looking into the theoretical explanation for the experimental behavior as motivated at the very beginning. The science is good only when I have multiple legs of science, experimentation, theory, and computation working together. So basic problem that I have is, or the approach that I'm going to have, is that I'm going to go back to this very basic Newton's law of viscosity setup with very simple situation. Situation is simple because I have only one direction of viscosity that is non-zero. Okay? For fundamental explanations, I don't need anything more complicated than that. Okay? And I'm going to impose the gradient in that velocity only in one direction. This cross direction will be y direction. Okay? And I'm actually assume a very simple gas in between to begin with. Okay? In that simple gas, so-called kinetic theory will be valid. Okay? And kinetic theory has its simplifications that I'm going to get to. And basically, I'm just going to impose this gradient, and I'm going to look to kinetic theory to give me, I'm basically going to fit kinetic theory into that tau yx is equal to minus mu dvx dy, okay? And see what I get for viscosity. Okay? And basically, any quantification that I have, I'm going to look to kinetic theory to give me that quantification. This is a general approach in research, if you will. So if I was doing experiments, I would take that assumed relationship, okay? I would measure what I can, so my experimental measurement would be giving me that force or area or separation that I need, or Vx, right? And then I can recover viscosity as necessary. Okay? In this particular case, I don't have an experiment, I have a thought experiment, which is kinetic theory experiment, so I'm going to look to kinetic theory, which is sort of statistical averaging going on, that will give me the measurements that I need. Okay? And I'm going to recover what I get for viscosity, and since this statistical theory gives me formulas, I'm hoping for a formula for what viscosity should be. Okay? Does that make sense as a process? So this is basically a fundamental research process that you possibly will do in your research as well. Okay? You will assume a model and try to fit things into, and then of course compare the two. Now, in difference is that in experiments, again, I would simply measure viscosity and just tabulate it. In theory, I'm hoping to get a formulaic solution, so something that I can plug in, might be pressure, maybe temperature, something about this gas, and get the formula for viscosity out. So this is where we're headed. Okay. So what about kinetic theory? My basic assumptions are that each molecule is a ball, and sort of like a tennis ball. It's bouncing around, colliding elastically. While it's colliding elastically, it's not losing any energy. Oops, well that's a simplification, but let's work with it, okay? And I don't have any other forces in the system, so there's no attraction of any force, of any kind. Now, if you've been through basic chemistry, you know that's not true. Okay? So that my molecules are not necessarily non-charged balls of any kind. But we will go with this simplification for now and see whether we can learn from it. And then final thing is that this gas is kind of rare. Okay? So I have fairly large distances between molecules. Okay? And there is enough of molecules in this box that I'm looking into that I can do a statistical average. So my theory is valid, or my theoretical formulas are valid. Okay? Sorry, okay, yes?
What do you mean a large distance? Like how large?
In gases, it's typically, so if I have a radius of the molecule like more than 10 molecular radii and above, let's say. But we'll actually get some formulas later for force and we'll actually see where that kind of is valid.
Okay.
But that's a great question. You always have certain assumptions and then but it's that those large distances between molecules that kind of allow you to look at them as non-attractive balls, because if they're that far away, then van der Waals will be like, well, too far. Okay. So for van der Waals, force is not important. Yes.
Are the elastic collisions perfectly elastic?
Yeah. Yeah. That's what I mean by elastic. There's no perfectly elastic. Elastic is perfect.
Okay.
So inelastic is not perfect in that sense. So yes, I'm not losing energy. So here is kinetic theory. Okay. So I'm going to impose this gradient in velocity, and here are my hypothetic balls moving around. Okay. And I'm placing things in a coordinate system. So I have velocity at y minus a, at y plus a, and I'm going to get to this separation a. Okay. So I need kinetic theory results that I'm not going to go in detail for, but you will actually have a homework exercise where you will actually compute one of these formulas just to see how it works. Okay. Just to get the feeling. It's a little bit of integration, really, not much. Okay. So my lambda is mean free path between two collisions. You're probably familiar with that one for gases, right? So I have mean free path, and it can typically be computed from the diameter of the molecule and also from the molecular number density of molecules. Okay? So this is number of molecules per unit volume. So if I have that, I can come up with my mean free path between two different collisions. Now, two different collisions, they're happening. So basically, after collision, between two different collisions for a molecule, I have this distance lambda. And let's say that it's like here. Okay? So one collision happened here, one collision happened here. Now, if I have that lambda, okay, this is not necessarily in coordinate direction, this lambda. It's in any direction. It's a randomized system. Right? So A is my sort of average distance in one of the directions, one of the coordinate directions between those 2 points. Does that make sense? So that A is slightly less, it's 2/3 lambda. Again, taken statistically. So theory actually goes and computes this. And these days, if I have the computation and I have a molecular simulator, I could actually go and throw in 100,000 molecules in a box and see whether I get lambda and A to be precisely this. That'd be a nice test for your molecular dynamics simulator. Do I make sense here? Okay. All right. So this is my kinetic theory results. And U is my average speed. Okay? My velocities for molecules, these molecules whizzing around, are randomly oriented in all directions. But they have a common average speed, which is the length of that velocity vector, and that's given, it's basically related to temperature. That should come to no surprise to anybody. Okay? The higher the temperature, the higher the average velocity. And mass, so this is mass, this is phi as in phi, and this is Boltzmann constant. So this is essentially related to my energy. Kinetic energy is proportional to kappa T. Okay? And finally, what I will actually need is, I have only 2 minutes left. All right, so I'm going to actually stop here. So Finally, what I will need is frequency of molecular bombardment. So if I may, okay. So this Z will be frequency of bombardment on one side of this surface, okay, not both sides, but one side of the surface. And where we will need it is we'll place this plane here at Y, and I'm going to look at all of the molecules that are, as they're bouncing around, moving up. I need the frequency of those moving up, because those are the ones that are transferring their momentum in upward direction. And those bouncing from the top of this same plate, excuse me, okay, from the upper direction, they're taking their momentum down, so I need a number of those too, and it's also a number of Z. So that's why I need Z. So this frequency of bombardment per one side of the air. Right. So we will continue this next time. I have just one question for you before we break for the class. So I mentioned that there will be some computational projects which you will have. I suggest MATLAB, but you will have a choice of computational software to use. Would it be helpful for everybody if I posted sort of MATLAB reviews, movies that you can work through on your own? How many of you have used MATLAB before? And not about a third of you never seen MATLAB? So especially for those who haven't seen MATLAB, are you motivated to learn it? You don't have to, but you will have to use something. Okay? So I will post the movies. Movies are actually, that's a review that Dr. Balhoff made for his research, for his reservoir simulation class. Okay? So I'm going to post that so you can work through those videos on your own pace. All right?